Okay, so now basically we have two more topics I want to discuss. One is inverse functions, because like I said, those are used in probability kind of like all the time when you start getting into the theoretical part of it. And two is what happens when a function acts on a set. And we already saw that a little bit with the image of a function, right? But so in this video, I just want to talk about inverse functions first. So I don't really want to talk about composition too much because there's not really a lot more to it than what we already talked about in Math Tools 1. And I think we already saw how powerful composition really is, which, basically like a lot of different functions can be thought of as a composition of two functions. We saw that with the transformations of the graphs and of course in inverse functions as well. So, I think we covered that pretty well, but I do want to go over the more technical definition of composition. It's not really technical, it's just what does the definition look like using these sets now in this like kind of new definition of functions. And the only reason I really even want to go over this is because, of course, inverse functions relate to composition. So let A, B, and C be non-empty sets. And let f from A to B, f be a function from A to B, and g from B to C, B functions. Again, you don't really need to write B functions because that's kind of what this implies here, but so it's a little redundant. But that's what this theorem says. So the composition of f and g is the function g, and then we put the circle f, so g composed with f, A to C. And we saw the different notations for this. We don't really use this notation a lot, of course. It's used a little bit more with these more technical aspects. Defined by g of f of x is equal to g of f of x, right? The more common notation that we saw. I don't want to say it's more common, but it's kind of my preferred notation. I don't really like the circle one. I don't really think it looks very good handwritten because it kind of is hard to distinguish from an O. Okay, so for all x in A. Okay, so we call this a composite function. So the idea now with the sets, the difference is A is mapped from A to, or F maps from A to B, G maps from B to C. So this new function, and maybe you give it a new name, like maybe you call it H or whatever, if you want to. Then H goes from A to C. So it kind of skips that middle function. It doesn't really skip it, right? Because you go through that function. So its domain and all that are still important, but the end result kind of looks like it skips over it, right? Even though it, in the background, B is still important. So function composition is really important in mathematics. It's particularly important in other branches of math, like abstract algebra, where in a part of that called group theory, function composition induces a group in the like set of all functions. So groups are really important because if you make a group, they all share similar properties. So you can show like function composition and basic things like addition and multiplication, all that. They all behave very similarly in that context. So I think it's a little more important in other aspects of math than it is, like in probability and statistics. Like they definitely come up just like in the algebra and stuff and in like graphing functions. So like the more basic parts of it, but I could be wrong, but just off the top of my head, I don't think it comes up as often in like the theory, depending on how you look at it, I guess. But it's just like one of those things that's kind of like always inherently there in the background because we can think of like most functions as compositions of functions. So it's good to kind of have a precise definition of it. So you can show some nice results with this definition. Like for example, you can use this to show that if F is an injection and G is an injection, then H would also be an injection. And if F is a surjection and G is a surjection, then H is also a surjection. And from those two, it follows that if F and G are bijections, then H is also going to be a bijection. Okay, so that's just kind of a nice little theorem you can prove with that. Which might be, maybe I'll put it on the homework problem or something because it's a nice proof to practice with. But for now, we're going to turn our attention now to inverse functions. So inverse functions, again, another thing we talked about in Math Tools 1, but it's just been so long since we looked at them that I think you'd be a little bit surprised going into like probability theory and stuff, just how often things are expressed in terms of inverse functions if we don't look at it again, just a little bit more rigorously. So before we do that, there's one more definition, which is another thing that we've used kind of a lot in this class, but we haven't actually called it this, and this is called the Cartesian product. So this relates to two sets. So the Cartesian product of two sets A and B is written as A cross B, and this is equal to the set of all ordered pairs such that X is in A and Y is in B. Okay. So we have used this. This is like how we define our domains for all of like the regions we were integrating over for multiple integrals. The domain for, two variable functions. And we've seen this, like I alluded to the fact that we call R cross R, R2, right? Right, so just kind of like use the same kind of notation we use when we normally multiply two things together and we get this squared, even though this multiplication, it's called a product, but it works very differently than like a typical multiplication where it creates ordered pairs rather than putting the numbers together. By the way, R2, you can actually show that it has a bijection with the complex numbers. So that tells us that the complex numbers in R2 behave very similarly. So the complex numbers including that imaginary number I. Right, I think we talked about that a little bit. We didn't like really go into it, but I think it did come up when we were talking about that sometimes you get roots that have this in quadratics, right? Or any polynomials. That was a while ago now. So anyway, the Cartesian product kind of gives us a framework now for considering a function to be a set itself. So this is kind of a theme in mathematics and theoretical mathematics where you're kind of trying to put everything into this framework of sets. And because of that, set theory, which is its own branch of math, kind of permeates through every branch of math. So like no matter what math class you're taking, whether it be analysis, which is like advanced calculus, or algebra, which I alluded to earlier, or probability, one of the first things you're doing is looking at the basics of set theory. Just because it's a good framework to kind of put everything in. So by that definition, we can view a function as a set. So f from A to B, this would be a subset, so I guess I should write it like this, of A cross B. And we can say it might be equal to, maybe not. So by this definition, we'd have f is equal to the ordered pairs A, f of A, such that A is in A, right? And it's given that f of A is in B as well. So sometimes this might be written a little bit differently. Sometimes this could be written as f equals A, B in A cross B, such that B is equal to f of a. Okay, but this is definitely an interesting way of viewing it, because now we're viewing functions as sets. So we know that functions kind of dominate, you know, like all of calculus and algebra. Like everything we've done has been in terms of a function, but now functions are sets. So that means everything we've done can be viewed as a set. In the next video, we're going to look at, what happens when a function acts on a set, when you put a set into a function. So this is like you're putting a set into a set. So now it's like function composition, because you're putting a set into a set, which are functions, right? So, it's kind of this whole loop now of everything feeding back into set theory, which is it's very interesting to me, because you can have, this is why you can have totally distinct branches of mathematics where at the heart everything is kind of everything's kind of like, it has the same like mechanics behind it. We're just using it in different ways in different areas, right? And like probability versus something like abstract algebra or graph theory or something. And this is why, if you look for papers on these things, you'll see lots of crossovers between the different subjects. And then they create more different subfields, like probability and graph theory, where you come up with random graphs, or statistics and physics, where you're looking at statistical mechanics. Right? So this is kind of the framework that allows us to put all these things together. All right, so let's get into the definition of inverse functions then finally. So let f be a function from a to b. The inverse of f, denoted f to the negative 1, right? So we should know at this point that's not actually like 1 over f, but rather just the inverse of f. It does use that notation because it, that's like the multiplicative inverse, but like the multiplicative inverse of something is that number to the negative 1. But it's important to keep them distinct based on the context. So f inverse is the set of ordered pairs BA in B cross A, such that same thing, B is equal to f of A. So comparing it to this definition up here, the condition over here is the same, B is equal to f of A, but the ordered pairs are just reversed, right? So that's not too surprising given our previous definition of a function. So we could also write this as B A and B cross A, such that AB is in F. Okay, now really thinking of F as a set here, right? Now, there's a few things that are interesting about this definition that might not be apparent at first sight. First of all, note that there's no condition on F for F inverse to exist, like we had before, right? The condition we had before was that F was an injection. That was what we needed for F inverse to exist. This doesn't give you that. It's just, this is the definition, which does not hinge on F being an injection at all. Also note that F inverse is not even called a function here, right? F inverse is just F inverse, right? F is a function, but there's nothing indicating that F inverse is a function. So that's the idea, is that in order for F inverse to be a function, we need F to be an injection. If it's not an injection, F inverse is still a thing, it's just not a function, okay? So when we were doing before, we were looking for inverse functions. But now we can think of F inverse as being a thing, being the set. It just isn't a function. It would still be a relation, which you have to think all the way back to the very beginning of Math Tools 1. Before we even defined what a function was, we defined a relation. And a function is a special type of relation, so it would still fall under that category. But regardless, we can still think of the set F inverse even if F is not an injection. So let me write down that F inverse is a function if and only if, and this part might actually be a little surprising, F is a bijection. Okay, so not just the injection. We do need surjection, but the surjective part is, we can kind of make that a little bit trivial by just restricting us to the space where it is a surjection, right? Because if F is not a surjection, then we can just change the codomain to be equal to the image, and then it is a surjection, right? We just restrict it. The injection part is a little bit harder. We saw that we can restrict the domain to make the inverse function, and that's still true. So, we can tweak the sets to make this a function if needed. It's a little bit easier to restrict B, because usually you only care about the part where it's a surjection anyway, because the rest of it, you don't even have any values. Whereas the injection part, you probably do care about the values where it's not an injection, right? So, but this is the technical definition, is that F inverse is a function if and only if F is a bijection. So note this is a two-way statement. So you could start with F being a bijection and show that F inverse is a function. Or you could start with F inverse being a function and show that that means F is a bijection, right? So these would all be good proofs to maybe practice with. Or they're shown in the textbook that I linked to. They're all written out there. So let's write this out as a theorem with a little bit more to it. Okay. So this says let A and B be non-empty sets and let F be a function from A to B, be a bijection, then F inverse from B to A is a function and for every A in A and B in B, F of A is equal to B if and only if, I'll abbreviate here, F inverse of B is equal to A, right? And we know this as our previous, this should have been F inverse of B is equal to A. And we know this from our previous discussion of what an inverse function is, right? The outputs and the inputs are switched. So no surprises here. So an immediate corollary to this, corollary is not a word we've used before, but you might have seen in other parts of math, but a corollary is just something that kind of follows immediately from the theorem preceding it, basically with no extra work, is one, for every x in A, F inverse of F of x is equal to x. And then two, for every y in B, F of F inverse of x is equal to x. Okay, so note the different order here, because the composition, it's going to matter which one is which, because you're going from A to B and then back to A. So F of F inverse, F inverse is going in to F, so it's going to be a function from B to B ultimately. And then F inverse of F is going to be a function from A to A. Okay. I'm sorry, this should have been a y here, right? Because we were using the y in B. So when we put that y in, y comes back out. Okay. So another interesting theorem that goes along with the inverse functions. Let f a to b and g b to c be bijections. Then g composed with f is a bijection. Okay, I already mentioned that before when we talked about composition functions. And a new thing here, g of f inverse is equal to f inverse of g inverse. Okay. So this is something we didn't really look at before. If we have two functions and we compose them and then take the inverse, that's equivalent to composing their inverses, but in a different order. So the inverse, if we're going to kind of quote unquote distribute it, which that is what it's called distributing it. You distribute it to the f and the g, but then it also reverses the order. Okay. And we saw kind of a hint of this when we were actually finding inverse functions, and we saw that the inverse function was using like the opposite operation. Like if the original function was using addition, the inverse was using subtraction. But if there were multiple of them, it also reversed the order of operations, right? So this is kind of the reason for that, which is that the inverse flips the order of the composition. So just to leave you with, after all this talk about inverse functions, well, where does this actually come up in probability? Which, of course, you'll talk about more there. But if you have a CDF, which is a cumulative distribution function, f of x, f inverse of x, or sometimes written f inverse of p, because, all right, so let me back up. Typically, f of x would equal some number p, right? It outputs a probability. So f inverse of p, which would output an x, is the quantile function, or sometimes just called the inverse CDF. Right, so this gives you the quantile that refers to that particular probability, or the number in the distribution that refers to that particular probability, which we call the quantile, right? So like in R, for example, if you used R, the programming language, this would be like the Q functions, like Q norm, Q binom, all of those functions. And this function doesn't actually always exist, meaning that, the CDF isn't always invertible. But you can still talk about this as an object. So maybe you put an asterisk on the word function here, but it's still a set, which we can talk about. And you can still use that set to give an alternate definition of the of the quantile function, using like some lower bounds on the set and stuff like that. So because the cumulative distribution function is not always increasing, which means it's not always injective, right? It only has to be non-decreasing, which means it could remain constant over an interval. So viewing this as a set gives us a nice framework then for defining it in those cases where it's not actually a function.